Hey everyone, this is a video on rotation and the correlation between polar and rectangular coordinates. I'm also going to be deriving velocity and acceleration from position, but that's only going to be in scalar terms. So the first thing I'll do is I'll show how x is equal to r cosine theta, and y equals r sine theta. And the reason for that is, the reason I'm explaining that is to kind of show you where these terms come from and how you can convert between polar and rectangular coordinates. So the first thing I'll do is I'll just draw an XY plane, and I'll draw a position with r. This is the magnitude of the displacement, so r, and we're going to define this as our opposite and our adjacent. So, and this will be sine theta. Oh, this will be theta, sorry. So if we define cosine theta first, cosine theta equals our adjacent over the hypotenuse, which is our position or the total displacement. So we can then say that this component here, A, is equal to r cosine theta by solving for A. We can do the same thing for our opposite by solving this equation here like so, the opposite over hypotenuse, and then make the opposite the subject, so r sine theta equals our opposite. Okay, after that, the next thing I'm going to do is defining what velocity is. So our velocity and acceleration. If we draw another plane here, say this is our position vector, and we know that this body here, represented by this line, is going to rotate counterclockwise, so this way. It's going to rotate that way. So if we've defined this as our position, if we look at the velocity at this instant, it will be going in this direction. So if we look at alternate angles, we can see that this angle in here is 90 minus theta, but if we're looking at a tangent, we can then define this angle to be theta, and if we define that angle to be theta, then this angle in here is also theta. So we'll just define it as being theta. Alright, so if we do the same thing, looking at our components like so, we can see that our velocity, or we know the definition of velocity is the time rate of change of displacement, so dr on dt. And this is going to be in the x direction. It's going to be dx on dt, which is equal to dx on d theta times d theta on dt, where this d theta on dt term is the angular velocity, which is also represented by omega. Our vy term is going to be done the same way, just represented by different term. Alright, so the velocity in the x direction is just, if we derive x with respect to theta, we end up getting negative r sine theta, and that's just multiplied by this theta dot term here. And the same thing is done for the y direction, so we get r cosine theta, theta dot. Now the velocity can be found, or the net velocity can be found by taking the square root of our components. So, or by using Pythagoras theorem, and that just gives us, well, sine squared theta plus cosine squared theta equals 1, and negative r all squared is going to be r, or the square root of negative r all squared is going to be just r, so this term ends up being r theta dot. If we then go ahead and take the derivative of velocity, so dv on dt, and we use the chain rule, so because we've already defined our derivative of position, or derivative of r as being r theta dot, we can then go ahead and say that this in here is going to be the time rate of change of r theta dot, which means that we derive our r term, so r dot theta dot plus r theta double dot. Now we know that r dot is just r theta dot, so this term here ends up being r theta dot squared, and our term on the right is r theta double dot, and that can be represented by r omega squared plus r alpha, which is our normal and tangential components of the acceleration. Okay, now that we've defined that, the next thing I'm gonna go ahead and do is to define what these terms are when we use vectors. So if we use vectors, we can use I and j terms as opposed to using components of direction like x and y. So we can define our position vector like so. This equals the magnitude of r cosine theta I plus the magnitude of r sine theta j. Now if we derive this with respect to time, we end up getting, we know that it's r theta dot, but we also know that this can be represented like so, where omega is in the k direction, so a positive angular velocity is out of the page. And the reason for this is, if we go ahead and substitute in omega k, so omega k cross magnitude of r cosine theta I plus the magnitude of r sine theta j, we end up getting, or we'll get omega, or magnitude of r cosine theta j minus omega magnitude of r sine theta I. Now if we derive our r term with respect to theta, we should get a negative sine and a positive cosine. Let's go ahead and do that. Which is the same, however it's just been multiplied by this omega term, which is the same, it's the same as what we get up here, but it's just not been multiplied by the d theta on dt term. So we can see pretty quickly that this is the case for our angular velocity. For angular acceleration, all it is the derivative of this term in here. Now I'm not going to do that, it's time consuming, but you can see that it's going to happen. If it happens in scalar terms, it's going to happen in angular terms too. Alright, thanks for watching.